Dear colleagues, dear panelists, I would like to welcome you to the webinar of the research project Helicopter Underwater Evacuation number 2, which is the final dissemination event of this project. My name is Willi Siegel and I act as moderator for this project webinar today, and I'm an employee of the European Union Aviation Safety Agency. For the start, let me please give you some contextual information on this project. This project started around 2 years ago. It has been funded by the European Union's Horizon Europe Research and Innovation Programme and was planned in the work programme 2022. It was planned as an indirect managed project for the delegation of the European Aviation Safety Agency. To this effect, the European Commission has formally delegated to EASA the contractual and technical management of this research project. Following of a public tender procedure, EASA selected a consortium which was led by CAI as the best suitable tenderer and awarded a contract for the implementation of this research project. The research action is part of an EASA-managed research project portfolio, and in our portfolio, where we have currently around 37 projects, we are dealing with aviation authority needs. And these research projects are an important pillar for EASA in order to perform our core tasks. Now, let me introduce our panelists. To my left, there is Emily Lewis. Emily is a member of the European Union Aviation Safety Agency. She's a senior expert in the certification directorate, and Emily acted as the technical lead in this project. Then I move on to Dave Horson. Dave Horson is a manager of the United Kingdom's Civil Aviation Authority, and Dave was acting as the technical lead from the contractor side. And last but not least, there is Dr. Hugh Shaw, who acted as a key expert in this project and was an independent consultant for the CAI. Now, let me please go to the agenda. We will start with Emily, who will provide a research scope and objectives debrief, explaining why EASA actually selected this topic and why we consider this as important. And then we will hand over to Dave and to Sue, who will brief us on the project implementation and the key results of this project. We will then move back to Emily, and Emily will be so kind and will explain to us how EASA will take this research project results further and how we would like to generate benefits out of that. Then, dear participants, we come to you with a question and answer session. For that, please note that we are using Slido, and you can use, and Slido is actually integrated into your WebEx application, and you can already use Slido in order to raise your questions or to raise your comments. We will then, in the question and answer session, go to all of them. After that, we conclude with some remarks, and we will then finalize with our webinar. So, let's start. Emily, please. Can I please?
Move to the next slide, really? You have
yes, we are still with.
You have to.
So, and there we are. Emily, it's yours.
Thank you, Willie. So as explained by Willie, the research project received funding from the European Union Horizon Research and Innovation Programme, and it was awarded to the UK CAA International. The overall objective was to address the safety recommendation from the UK Accident Investigation Branch following the Super Puma accident on approach to Sunborough Airport in the Shetland Islands in August 2013. So this safety recommendation asks that is it recommended that the European Aviation Safety Agency instigates a research programme to provide realistic data to better support regulations relating to evacuation and survivability of occupants in commercial helicopters operating offshore. This programme should better quantify the characteristics of helicopter underwater evacuation and include conditions representative of actual offshore operations and passenger demographics. I will explain more about the background and the tasks of this research project in the following slides. So the contract has a total length of 2 years and was valued at a little over €500,000. More information can be found on the dedicated internet site, which following this webinar will include a link to this presentation and the webinar recording. So as an initial response to the safety recommendation, EASA launched a research project in 2019, which was also performed by the UKCAA International. The final report was completed in November 2020, and the comprehensive report is published on the EASA website. The objective of this research was to carry out an initial review into the nature of the research that could be envisaged to answer this safety recommendation. So the first task of this project was to perform an analysis of the currently available information. The shortfalls in this data were then identified and future research activities proposed to address these shortfalls. The initial research project identified 3 high potential safety benefit future projects. The first one was an investigation into the forces required to jettison push-out underwater emergency exits. The second one was underwater escape from the cabin with a full complement of passengers. And thirdly, passenger training and fidelity. Of these 3 potential projects, 2 were selected to be investigated further by this research project, the helicopter underwater escape number 2. So the first task, forces required to jettison the underwater emergency exits, aims to evaluate the influence of being underwater on the required force and determine the maximum force that a person could apply to the exit. An appropriate maximum force can then be established, confirming the current AMC or proposing a future revision. Task 2, underwater escape with a full complement of passengers, aims to quantify the escape process and determine if the expected 60-second escape time is achievable. This will validate the current requirements or lead to a proposed update. If regulatory action is considered necessary based on the conclusions of this project, the subsequent rulemaking task could consider updates to rotorcraft initial airworthiness, so CS27 and CS29, the AirOps rules related to rotorcraft ditching or offshore operations, the ETSO for ditching survival equipment, such as the emergency breathing system, Part 26 to evaluate the retroactive requirements for rotorcraft ditching operations, and also the SC VTOL MOC, which has been based on the rotorcraft requirements for ditching certification. In addition to the EASA rulemaking activities, Task 2 aims to fully address the safety recommendation. So I'll now pass over to the colleagues from UKCAA International to present the project implementation and key results.
Good afternoon, everybody. The trials performed for the project were carried out at the helicopter underwater escape training facilities of Blackpool and the Field College at their Fleetwood Nautical Campus. The trials were run by the staff of the Fleetwood Test Laboratory, and the helicopter simulator was operated by the training staff of the Fleetwood Offshore Survival Centre, who also supplied the safety personnel and divers. The environmental training tank in the photo on the left consists of a 4-metre deep pool with an adjustable shallow water platform. We will now play a short video clip to give you an appreciation of how the simulator operates. The helicopter underwater escape training simulator, or HUE2, that you can see in the photos is normally configured with 2 large doors at the front of the passenger cabin and 4 underwater emergency exits. The normal seating arrangement is 2 rows of 3 seats arranged in a 2+1 configuration, with a third row of a single seat, plus 2 seats in the front cockpit compartment representing flight crew seats. The high back seats are fitted with 4-point harnesses and can be moved to accommodate different seating configurations. The right-hand photo shows a 4 abreast configuration used during the trials, with one of the seats in the stroke position. The back of the cabin is open to allow access and to permit the HUE2 instructor and safety divers to observe the test subjects inside the HUE2. A pool of 18 test subjects was recruited by the Fleetwood Test Laboratory, selected to be representative of the offshore workforce. The size categories defined in the new survival equipment standards were used to classify the test subjects, and at least 2 subjects for each of the 9 size categories were selected. At least 2 subjects had a shoulder width measurement greater than 500 millimetres, which equates to the UK North Sea Extra Broad, or XBR, classification. There were also a range of ages and a mix of males and females. All test subjects wore a helicopter immersion suit with a thermal liner and a helicopter constant wear life jacket, both similar to the equipment used by members of the UK offshore workforce when flying offshore. The survival equipment was worn over standard clothing, and the life jacket was fitted with an approved Category A compressed air emergency breathing system. Full risk assessments were undertaken before conducting the trials, and ethical approval was provided by the Blackpool and the Field College Ethics Committee, based on the risks identified. All test subjects were given information on the purpose of the trials, what they would be expected to do, and their right to withdraw at any time. All test subjects undertaking wet trials received training in the HUE2 based on the helicopter safety sections of the HUE2 Basic Offshore Emergency Response Training. Additional training in the use of compressed air EBS in the helicopter simulator was undertaken following the methods used for Canadian basic survival training. A review of helicopter underwater emergency exits was performed to ensure that the exit designs selected for the trials were representative of the European offshore helicopter fleet. The majority of in-service offshore helicopters are fitted with push-out window underwater emergency exits, most of which include removable pull-out strips to facilitate jettison of the window. The only other exit type currently in service on offshore helicopters is the lever-operated hatches on the Sikorsky S-92, which make up a significant proportion of the current offshore fleet. There are a variety of underwater emergency exit sizes and shapes on current in-service helicopters. However, the minimum unrestricted size is the 19 by 26 inch Type 4 exit, or an aperture capable of admitting a 19 by 26 inch ellipse. This is also the minimum size required by the certification specifications from Amendment 5 onwards that the research is seeking to validate. Exit size was expected to influence escape time, which is especially relevant to Task 2. The certification specifications also allow the use of an exit large enough to permit the simultaneous escape of 2 passengers side by side, which, in theory, would require an opening of 26 by 38 inches. Advantage was taken of the opportunity to evaluate these exits and also to assess whether the orientation of the exit is important, that is, landscape or portrait. Taking account of the results of the review and the aims and objectives of the research, a Type 4 size push-out window exit similar to the Leonardo AW189 rear passenger exit shown on the left was selected. A Type 3 size lever-operated exit similar to the Sikorsky S-92 escape hatches in the right-hand photo was also selected. At 20 by 36 inches, the Type 3 exit is not quite as large as the double exit specified in the certification specifications, but it was considered of value to assess whether this standard exit would be large enough to permit the simultaneous escape of 2 passengers. The 4 standard exits in the HUE2 are Type 4 size, and it was only necessary to replace them with new exits fitted with adjustable spring ball detents so that the jettison force could be varied. An example is shown viewed from both inside and outside the HUE2 in the photos. A special adapter plate was also manufactured to enable an actual AW189 rear passenger exit to be fitted to the HUE2 to enable comparison between the simulated exit and a real aircraft exit. This was to confirm that the behaviour of the simulated exit and a real exit, secured by ball tents was sufficiently representative of a real exit fitted with a rubber seal. It's not practical to produce a variable force rubber seal. The comparison was performed by 3 test subjects separate to the main pool of 18 in order to avoid any practice effect on the main trials. The 3 operating techniques of hand push, hand strike and elbow strike were evaluated for 4 points of force application on the exit. These were the lower corner, halfway along the short side, halfway along the long side, and in the middle of the exit. The trials were performed with the seat at normal height and then repeated with the seat fully stroked. The force applied was measured using a load cell for the purposes of the comparison. The operating force of the simulated exit was adjusted to match the aircraft exit for a hand push at the lower corner. The comparison confirmed similar behaviour of the real and simulated exits. In particular, for both exits, the optimum point of application of force for the hand push and hand strike techniques was found to be the lower corner of the exit. For the elbow strike technique, it was the middle of the long side of the exit. The middle of the exit required the largest operating force in both cases. The simulated Type 3 lever-operated exit was fitted to the port side front door frame using a special adapter plate as shown in the left and middle photos. The operating force was adjusted by varying the torque loading on the lever spindle, which in turn varied the friction and hence the operating force. Comparison with a real aircraft exit was not considered to be necessary. The starboard door frame was fitted with baffle plates to present a 26 by 38 inch large exit in portrait orientation for use during Task 2. This exit utilised the normal HUE2 operating lever located at the top of the door. And now on to Task 1. As Emily mentioned earlier, the overall aim of Task 1 was to establish the forces that human test subjects are capable of applying to operate underwater emergency exits when they are inside a flooded and inverted helicopter cabin. The data generated by the trials can then be used to establish an appropriate maximum permissible operating force for comparison with the certification specifications. The methodology employed was to implement simulations of representative underwater emergency exits in a HUE2 in a way that allowed the operating forces to be varied and then perform human subject trials to establish the worst case maximum permissible operating forces. The testing of the Type 4 push-out window exit commenced with dry trials and employed all of the 18 test subjects. The maximum operating force for each test subject was determined with the seat in the normal and stroke positions using the corresponding optimum point of force application previously established for each of the 3 operating techniques. The wet trials were performed with the seat in the worst case position as determined during the dry trials, which was the stroke position. All 3 operating techniques were assessed by 9 of the test subjects, 1 from each of the 9 size weight classes. Each technique was performed with both the left and right hand or elbow. Each wet trial was performed with the underwater escape exit fully submerged but not inverted. Compressed air EBS was used by the test subjects during these trials, which was deployed prior to submersion. For each test point, the operation of the exit was undertaken with the test subject in each of 3 starting positions, representing the possible scenarios that might occur in a real underwater escape. These were seated next to the exit, floating in the cabin with the use of a handhold on the cabin wall next to the exit, and floating in the cabin without a handhold. Finally, the worst case scenario was repeated with the addition of a capsize immediately prior to exit operation. There we go. As for the Type 4 push-out window, the testing of the Type 3 lever-operated hatch commenced with dry trials and employed the same test protocol, except that there was only one operating technique to evaluate. The wet trials also followed the same protocol, except that the effect of gloves was also evaluated. There are some general points regarding the test protocol for both exits worth a mention. Firstly, the dry trials were started at the FAA AC operating force of 55 pounds and were reduced in approximately 5 pound increments until all test subjects were able to operate the exit. If all the test subjects were able to operate the exit at 55 pounds, the operating force was increased instead of reduced. Secondly, the wet trials were started at the lowest maximum operating force established during the dry trials in the expectation that exit operation would be more difficult in the wet condition. Third, during both the dry and wet trials, test subjects that had already successfully operated the exit were not required to repeat the test at lower operating forces. This was simply to save time. And finally, the sequence of completing the trials was randomised across the subject group using a Latin square to avoid any order effects. As you can imagine, with 18 test subjects and a number of permutations of variables such as seat position, left hand, right hand, and Jettison technique, there are hundreds of results. But the results of most interest are the worst case or lowest forces measured, as it is these that represent the limit of what occupants can be expected to cope with in an emergency. In terms of the overall results then, for the Type 4 push-out window, the worst case was found to be under wet conditions, seated with the seat in the stroked position and with the exit to the right of the test subject. For the Type 3 lever-operated hatch, the worst cases were found to be under wet conditions in the two starting positions of, firstly, seated with the seat in the stroke position and with the exit to the left, and secondly, free floating in the cabin. And here the chart shows the lowest maximum permissible operating forces for the two exits. From left to right, they were 40.5 pounds for the hand push and hand strike on the push-out window, 61 pounds for the elbow strike on the push-out window, and 35 pounds for the lever-operated hatch. Note that all of these forces, except for the elbow strike on the push-out window, are lower than the FAA AC figure of 55 pounds. Some general findings of interest were that gloves didn't have any significant effect. They were only evaluated for the lever-operated hatch, but this was because they were not expected to make any difference when operating the push-out window. Secondly, handholds were very useful for operating the push-out window when free-floating in the cabin, but made no difference with the lever-operated hatch. Third, the addition of the capsize didn't have any effect on the operation of either exit. Finally, some test subjects couldn't reach the lower corner of the window with the 4-point harness fully secured. This is important as it is standard practice to open the exit before releasing the seat harness. For the purposes of the trial, a 2-point waist harness only was worn by all test subjects. Turning now to the application of the results for the push-out windows, the lowest maximum permissible operating force of 40.5 pounds using the hand push and hand strike techniques was lower than the limit defined in the FAAC, which is currently applied by CS 2729. However, the lowest maximum permissible operating force for the elbow strike technique of 61 pounds was greater than the FAAC load limit. So, either the force limits in CS 2729 should be lowered for certification testing, or, if the current force limits are to be retained for certification testing, operationally, passengers should be briefed to use the elbow strike technique to operate the exit. Because of the dynamic loading situation, the operating forces measured for the hand and elbow strike techniques were highly variable. The static loading of the steady hand push technique was more repeatable, produced more consistent results, and should therefore be used for certification testing. Moving on to the lever-operated hatch. At 35 pounds, the lowest maximum permissible operating force was lower than the FAA AC limit. So, once again, either the force limits in CS 2729 should be lowered for certification testing, or some other means of ensuring that the operating force is acceptable should be applied for certification testing, or if the current force limits are to be retained for certification testing, some form of operational mitigation should be applied. And finally, there were some general regulatory points. Firstly, on handholds. These were found to be very useful when operating the push-out windows when the test subject was not secured by a harness. Handholds should be located so that they can be reached by passengers free-floating underwater in the capsized helicopter cabin to help overcome the buoyancy of the immersion suit and react against to operate the exit. Secondly, referring back a couple of slides, the relative positions of the seats and the exits needs to be arranged such that the occupant can reach and operate the exit with the seat harness fully secured. I will now hand over to Sue to take you through task 2.
You have to use the computer for the text and this for the screen. Sorry about that, some slight technical issue there. So for task 2, as mentioned earlier by Emily, task 2 addressed the safety recommendation which called for better quantification of the characteristics of helicopter underwater escape under conditions representative of actual offshore operations and also representative of passenger demographics. This task was split into a number of objectives. First, we wanted to measure the overall escape time for a full complement of passengers, and in so doing, validate the target 60-second escape time described in the AMC to the Helicopter Offshore Operating Rules, HUE2. Second, we needed to use seating configurations that were representative of the European offshore fleet. During the escape, we wanted to determine the escape routes taken and the exits used and assess the difficulty of escape. And there was a further objective to validate whether 2 occupants can escape simultaneously through a large double ellipse exit, as described by Dave earlier. And I'll be saying a bit more about this in a minute. And then finally, we wanted to look at the effects of blocking one or more of the exits. So the first objective to be addressed was validation of the large double ellipse exits. These trials were conducted to determine whether 2 occupants with shoulder widths greater than 500 millimetres could escape through an exit encompassing 2 ellipses of 0.48 by 0.66 metres, with the overall dimensions of 0.96 metres by 0.66 metres, as described in AMC1 to the certification specification CS29. Trials were undertaken with 2 pairs of large test subjects, as I said, with shoulder widths greater than 500 millimetres. We assessed attempts at simultaneous escape with the exit in both landscape and portrait orientations, using a test rig fitted to the back of the helicopter simulator for the landscape option, and that's the photo you can see on the left of the screen. On the right, the top 2 photos show 1 pair of test subjects escaping through the landscape version of the exit. Initially, the test subjects are facing each other, but while starting the escape together, the subject on the right pushed through a little bit more quickly, and also turned face down as he egressed through the exit. The second subject was just a little bit behind, but this escape was considered to be simultaneous. The two photos at the bottom show escape through the large exit in portrait orientation. A simultaneous escape proved a little more difficult as the test subjects had to battle against buoyancy while trying to escape together. They eventually opted for the technique shown, which is with one test subject positioning himself above the other. In each case, simultaneous escape was possible, and the escape process was not considered to have been hindered by the size of this double ellipse exit, validating the ANC material in the HUE2 rules. Next, we looked at the issue of seating layouts. A variety of passenger seating layouts are found in current in-service offshore helicopters. The results shown here are based on work undertaken by the UK CAA in their 2014 Offshore Safety Review. Based on this review and current requirements, we decided to assess escape from seating layouts with either 3 or 4 seats in a row. Some other layouts had seating across the cabin, while others had an aisle between the seats, and we wanted to reproduce this in the trials. We also wanted to assess the so-called club layout, shown for example in the AW139, the right bottom of the photo, where 4 seats face 4 other seats. Based on this review, we undertook a series of seating arrangement trials to determine the time taken to escape from these different seating configurations. The seats were aligned with the exits, and the exits themselves were either type 3 or type 4, depending upon the configuration assessed. And these trials were done with the helicopter inverted. So the first 3 of these trials looked at escape from a single row of seats, both without the use of a handhold and with the use of a handhold. I'll initially focus on the escape times without use of a handhold. So it took a mean time of 25 seconds for 2 subjects to escape from one type 4 exit. We then added a 3rd subject sat across the aisle, with all 3 using the same type 4 exit. And this took an additional 10 seconds on average for the 3rd person to escape. When we had 4 subjects escaping from 2 type 4 exits, the mean time for all to escape was 33 seconds, which is somewhat longer than the equivalent 2 subjects through one exit. Only very small differences were seen when we looked at the total times to escape when a handhold was present. When we compared the times for each test subject to escape with and without a handhold, the only significant difference was seen in the 3rd single row exercise when escape was quicker with a handhold. Yes, with a handhold. Sorry. Moving on to the double row trials, we first had a club arrangement of 2 subjects facing 2 subjects, escaping through a single large double ellipse exit. This took 39 seconds, which is longer than the 25 seconds for 2 subjects to escape through the smaller type 4 exit. It should be noted that there was no handhold on this exit. Also, as this was a push-out exit, there was a pull-out strip simulated, which again, because of the size, took longer to remove than the ones on the smaller type 4 exits. So, while the large exit potentially allowed the simultaneous escape of 2 subjects at a time, in these trials, they were a bit slow getting out, and the time was not equivalent to 2 subjects escaping through a type 4. I should also say that our test subjects were on the whole very calm and benefiting from the use of the EBS and appeared to take it in turn to escape without panic. And we wouldn't expect that in a real emergency accident. If I can jump to the 3rd row of this chart now, a similar escape time was seen for 8 subjects escaping through 2 type 3 exits, one of which being the double ellipse exit. A slightly quicker time was seen for 6 subjects escaping from 2 type 3 exits, which is row 2 on this table. And then the last 2 rows show the escape of 6 and 7 subjects through 4 type 4 exits. In each case, more rapid escape was seen with these configurations. Based on the single row results, we might have expected escape times of 25 seconds with no more than 2 subjects per exit. These slightly longer times may be explained by subjects taking a little longer removing the pull-out strips or fumbling with their harness, the 25 seconds representing an optimum time. Finally, the escape times with and without a handhold were not significantly different in these double row trials. Having gained experience with the seating trials, we then moved on to the full cabin escape trials. For these, we use a seating configuration shown on the right, with 4 subjects at the front of the cabin facing back, in a club seat arrangement with a further 3 subjects facing forwards. And we needed to maintain an aisle to allow safety swimmers to easily reach these subjects if necessary. These 4 subjects were served by 2 type 3 exits, E1 on the port side being the lever-operated hatch, and E4 on the starboard side being the large double ellipse exit. Behind them were 2 rows of 3 subjects served by 4 type 4 exits. As we were only able to seat 13 subjects within our particular helicopter simulator, we had a further 4 subjects in the water at the back to make a total of 17 subjects. And these 4 entered the cabin from the rear when submersion or capsize was complete. And they were allowed to use any exit they chose. This was thought to be equivalent to having an extra row of seats at the back of the cabin and those back exits being blocked. 4 of the seats you may see are marked with an S, and these were fixed in the stroked position. You can see the low position of seat 13 on the right of the photo. All subjects were using EBS, which was deployed prior to submersion. Using data from Task 1 work that Dave described, exits were set close to the maximum permissible operating force. So we had a force of 45 pounds on the Type 4 and a force of, I think, 40 pounds on the Type 3 exit. Escape time was measured from the point of submersion when the water reached the bottom of the window, just before the heads of those in the stroke seats went underwater, to the point when each subject surfaced after escape. So the first exercise was a submersion. On the right, you can see a diagram of the escape routes taken and the order in which the subjects escaped. The first person out of each exit is represented by the longest green arrow. The last subject to escape from each exit is shown by the shortest arrow in each case. At the front of the cabin, you can see that 5 subjects escaped through the Type 3 lever-operated exit, E1, and only 2 subjects escaped through the double ellipse exit, which is E4, this taking a little longer to jettison. In this exercise, the subjects in the 2 back rows all escaped in order through their nearest exit. The 4 subjects swimming in from the rear each selected a different exit. So the first subject into the cabin was 6A, was the 3rd subject to escape through exit E5. The second in, subject 4B, was the 2nd to escape through exit E3. The 3rd in, 9B, was the 2nd to escape through exit E2. And the 4th in, 6B, was the 3rd subject to escape through E6. Overall, the first subject out was 8A, who was seated next to exit E6, and he took 8 seconds to escape. The last person out was 7B, who was seated in the stroke seat at the front, who took 35 seconds to escape. He took longer to escape than the 4 coming in from the rear, and the video footage showed that he waited for others to escape, remaining very calm throughout. The swimmers moving in from the rear commented that the aisle was a bit narrow to move through, and we'll see more evidence of this a bit later. Next, we undertook a capsize exercise, and I'm first going to show you some video from above and inside the cabin, with the 2 cameras inside the cabin showing the cabin in the inverted state. And I'm going to go on later to show you individual shots from inside the cabin to get a bit more detail. That's the capsize just completed. You can see the subjects from the rear of the cabin coming in after the others have escaped. In this case, the buoyancy from their suits is pulling them up actually towards the floor of the cabin, which is uppermost. Okay, I'd now like to play you the 2 videos from inside the cabin, but in this case in the non-inverted format, which I think is a bit easier to see what's happening. But remember now that buoyancy is pulling subjects to the floor of the cabin, at the bottom of the view, rather than the other way around. So first of all, the forward-facing camera. So capsize ends when we stop seeing a lot of bubbles. We found that the type 3 exit on the left was jettisoned ahead of the double ellipse exit on the right. Now you can see one of the subjects coming in from the rear of the cabin. He kicks 7B as he turns to go out through the type 3 exit. And then here's our smallish subject 1A. You might see is really struggling to release her harness. And she's eventually helped by one of the safety divers. She might have been somebody who didn't escape in a real accident. Okay, oops, gone too far, sorry. I wanted to play my second view.
You go back again. Yeah, and go forward.
I should say this worked earlier, folks.
There we go.
Yeah. Right, so this gives you more of a view of the subjects moving in from the rear of the cabin. You might be able to see the pull-out strip being removed from the large double ellipse exit. And at 1.7B appeared to be pull himself to the exit before he'd actually released his harness. I don't know whether you spotted that. And now we can see the subjects from the rear, quite struggling to work against the buoyancy and to manoeuvre themselves to the exits. That's the last one out. So in this first capsize, 6 subjects escaped through exit 1, the type 3 on the port side, and 3 through the double ellipse exit on the starboard side. Overall, the first person out was 2B, who was sat in the rear single seat on the port side. He took 19 seconds to escape in this case. And the last person out was subject 6A, who was the last subject entering the cabin from the rear, who escaped from exit E2 in 65 seconds. In our final exercise, we did a second capsize trial, but in this case we blocked the forward port side type 3 exit, E1. So this resulted in 8 subjects escaping through the large double ellipse exit and 7 subjects escaping through the type 4 exits. The first subject out in this case was 8B, sat in the rear starboard seat, who escaped in 23 seconds. And the last subject to escape was 9B. He was again somebody actually coming in from the rear. So he escaped in 70 seconds. So this exercise with a blocked exit thus took 5 seconds longer than the previous capsize exercise, where we effectively simulated 2 blocked exits. In this case, we simulated 3 blocked exits. When considering the overall escape times following capsize of 65 and 70 seconds, a number of factors should be considered. First, the exercises were undertaken in daylight conditions, both to enable filming, enable us to work out escape routes, but also to improve safety. Second, our subjects were mostly well trained by the time we undertook these full cabin exercises. Members of the European offshore workforce generally only undertake training every 4 years and without the repetition that they had here. In these trials, subject had the benefit of compressed air EBS, and again for safety reasons, EBS was deployed prior to submersion rather than underwater, the latter being more likely in a water impact followed by immediate capsize. Therefore, 10 seconds should be added to the escape times to allow for underwater deployment. However, to counteract this additional time, if we'd had another row of seats to use at the back of the cabin, then the 4 subjects who swam in from the rear would probably escape much more quickly, and this could have taken 10 to 20 seconds off the overall escape times that we found. To finish, I'd like to consider how the results impact on current regulatory issues. The results of Task 2 support the material provided in the AMC2 SPA-HOFO, which states that it should be possible for a full complement of helicopter passengers to escape from the inverted helicopter within the underwater survival time of 60 seconds. This conclusion is based on the best case when environmental conditions are good and nothing goes wrong. The additional blocked exit did in our trials increase escape time, but in the various exercises, escape times were also increased by problems releasing an exit, pulling out a strip, or releasing a seat harness. So there's a lot of variables that can increase the overall escape time. Thanks to the current design specifications, we did not observe anyone having problems escaping through an exit because it was too small. We found that an exit which provides an unobstructed area that encompasses 2 ellipses is large enough to permit the simultaneous egress of 2 broad-shouldered passengers, supporting the material included in the helicopter offshore operating rules. Based on our observations with the double ellipse exit, we have recommended that the term side by side should not be used in the regulations when referring to the double ellipse exit. The term appears to be ambiguous, and the important factor is that the simultaneous escape of passengers is possible. A very positive observation of the research team was that use of compressed air EBS allowed test subjects to stay calm and escape without signs of panic. And lastly, we found that the width of any aisle will affect the difficulty of escape for passengers having to move between rows, which is most likely to happen if an exit is blocked. Thank you. I'll now hand you back to the EASA team.
Thank you so much, Sue and Dave, for your explanations how you did this project. It was really scary pictures you have shown. Thank you so much for that. I hand over now to my colleague Emily. Emily, what are we going to do now with the researchers?
Thank you, Willie, and thank you again to Dave and Sue for the good feedback and the interesting trials. So I'll now summarise the benefits of this project and proposed future activities. So as a reminder, the main objective of this research was to confirm the current requirements in AMC material or to propose areas where future revision should be evaluated. Regarding rotorcraft initial airworthiness, the research project has largely confirmed the related ditching and occupant survivability requirements that were reduced in the Amendment 5 revision. This is a very positive result. However, there are a few aspects of the AMC material to be reviewed, such as markings on the handholds and appropriate maximum forces for lever-type mechanisms. The research has also generally confirmed the Part 26, AirOps and ETSO requirements, and this is also a very positive result. Regarding SC VTOL, the ditching operation MOC should be reviewed for overwater operations regarding handhold markings, emergency exit opening mechanisms, and also potentially the aisle width requirement if the aircraft could be fully submerged. So regarding the timescales, the recently completed new flotation system EASA research carried out by Darth Aerospace has already resulted in the launch of Phase 3 of the Rulemaking Task 120 and an update to the EPAS. This rulemaking activity is currently ongoing with the aim of publishing an NPA for public consultation regarding initial airworthiness in Q1 2025. And the DART new flotation system research also led to a review of the SC VTOL MOC material for ditching certification. So as this helicopter underwater research project addresses the same overall topic of occupant survivability in the event of a ditching or survivable water impact, the review of the initial airworthiness AMC material for rotorcraft will be included in the already active Rulemaking Task 120 Phase 3. Therefore, any update to the AMC material considered necessary can be included in the same NPA. Alternatively, we will consider any update to the AMC in the next regular update of CS 27 and 29. And likewise, the SC VTOL review will be carried out considering the conclusions and recommendations of both the research projects together. And this MOC is expected to be updated in Q2 of this year. So to summarise, the research project has fully addressed the safety recommendation from the UK accident investigation of the Sunborough accident in August 2013. The current certification specifications, CS27 and CS29 and CS-ETSO, have been confirmed, and this again is a very positive result. In addition, the rulemaking ditching AIR-OPS and Part 26 regulations do not require further rulemaking activity related to underwater escape. CS27, CS29 AMC material will be reviewed. This rulemaking activity will be included in the already activated rulemaking task phase 3, with a target NPA publication in the first quarter of next year for public consultation. And finally, the SC VTOL MOC will be updated according to the research recommendations as appropriate. So thank you very much. I will now pass back to Willie.
Thank you, Emily. Great results, and actually also a good outlook how we can use the results, and actually that the results confirm a number of our current requirements. I have in the meantime recorded 2 questions, and I would like to start with the first one from Lydia. And it is a question to first capsize. And Lydia says the results did not take into account the fact that one person did not manage to release herself, question mark. Sue, I think you will be the one.
Yes, we included the time that it took, but yes, I mean, overall, anything going wrong could have resulted in somebody not getting out in the real situation, so.
Yeah.
It's a very valid observation.
Yes, indeed. Yeah, thank you, Sue. There is another question from Grant. Did you consider the 92 style exit in an inverted position?
I'm assuming he means, does he mean the hatch? On the S92, of course, there are the push-out windows, and there are also the Type 3 lever-operated hatches. So the lever-operated hatches we did simulate.
Yeah.
Actually, Grant made a second part, which I just saw now.
Okay.
So almost as 92 have push-out windows in the large Type 3 exit, and I'm not sure staff are trained in the HUE2 to open exits. Was this considered?
So not trained with a lever. Yeah, that is true, and this project wasn't looking at training specifically. So there are some learnings for training out of what we did, but we weren't specifically looking at training. But no, he's correct that most training doesn't cover the lever-operated hatch.
And if I may add as well about the S92 windows. So as we know, we have the lever arch larger windows on the S92, and we have the smaller windows, which are the push-out windows along the cabin, which are smaller than our current CS27 and 29 regulations. And what we found for the scope of this research, what we had asked UKCA International to do and what's in the tender, is to validate our newest requirements. So our newest requirements dictate that these windows would be called underwater emergency exits, and they would have to meet the Type 4 requirement for CS29 or the ellipse requirement for CS27 types. What we didn't want to do is extend further and have a look at older type designs which are not compliant with today's CS requirement. So that's why they weren't included. The smaller windows were not included in the scope.
Yeah, just coming back to Grant's point, though, I think it's fair to say it's my understanding that the passengers are trained to use the push-out windows. That I don't believe that, because in fact I believe most of the hatches also have a Type 3 push-out window installed in them. So I think for simplicity and for consistency, passengers are trained to use the windows, not the hatches, the lever-operated hatches, although of course they are there if needed.
And also add to the training. So the first helicopter underwater escape, which was the document review and recommendation of 3 areas, included as a 3rd area training. That was not included in the scope of this research project because it's not currently under EASA responsibility. We focused on certification requirements AirOps requirements, Part 26 requirements, and also what we could learn for SCVTOL. So training was deliberately kept out of the scope, but the final report will contain some recommendations should somebody want to consider it for their training operation, their training procedures.
Thank you very much, colleagues. Now, Stuart, thank you very much for forwarding a question which Tim actually raised in the webinar chat. So his question was, what difference is estimated in escape times should they be done in the dark? Good question, isn't it?
It's a very good question. We were kind of half expecting a question on whether or not how realistic the exercises were in terms of day-night, and I think it would have been really great to have done some trials in the dark, but from our starting position of the full cabin escape trials never having been done before, I don't think we would have successfully got that past the ethics committee, in particular because the safety divers cannot see what's going on.
Yeah.
I think it's fair to say logically one would expect the escape times to be longer. Of course, they will have the EXIS lighting system there. It's an interesting question. Longer, but by how much? I wouldn't like to say, and that might be something for future trials if anybody's brave enough to attempt it.
And also, as you said, Dave, the lighting, the darkness may be compensated from the heels lighting, which is now included in the requirements, the Part 26 and the AirOps regulations. So it would have been an interesting study to have done, but it was going beyond what we wanted to put in the scope of this research.
Yeah. I think also anything like that does actually cause more panic in people. Sometimes that means they'll escape more quickly.
Mm.
So it'd be more difficult. It's much more likely that things could go wrong and people not get out. But some of the escape times actually could be quicker in the dark because people are panicking more. So it's a very complex thing that without doing a lot of repeated trials, which again increases the risks, this is difficult. So it's quite a difficult one to predict the effect that the light conditions would have.
Thank you. I mark also this question as completed, and we have another one, and which is actually the last one in my list here. And I see here that a colleague is saying Slido is blocked. Okay, colleagues, if this is the case that Slido is blocked, please be so kind, use the WebEx chat function, and we will certainly also look into this one. So there is, at least in my list, and I see there will be another one. Janne says, what type of handholds are used in the trials, and when were they and where were they located?
Yeah, well, a handhold was just a simple grab handle, like I guess a draw pull, effectively, designed to be large enough to fit a gloved hand on, and they were located at the lower corner of the window. So they need to be on the lower corner so that the occupants can reach them when the cabin's upside down and the occupant is floating up under the buoyancy of the immersion suit. So they need to be towards the bottom of the window, which means that once inverted, they are towards the top, which is where the passengers are going to be. So there's a bit of a trade-off there between having them to hand, but also they mustn't interfere with the passengers in the normal position. This is described in more detail in the report.
Yeah.
And they were marked in our case. We simulated marking with black and yellow tape.
Yes, I don't believe currently they're covered by the AMC to have the black and yellow markings, but that's something that I think the EASA is going to look at.
Yeah. Thank you. Another question from Grant. Was there any issues identified with the seatbelt person who could not escape?
I think I think it's on previous trials where we've had issues with seatbelts not undoing. It can be because the seatbelts are getting dumped every day, several times a day, and there can be maintenance issues with the seatbelt. Exactly what the issue was in that case, I don't recall. So whether it was an actual equipment issue or whether it was just the test subject not getting it right, We don't know. That's something perhaps, I don't know, is Brooke on the line? Does Brooke know? No. We don't know Brooke.
I don't remember any feedback in the questionnaire in terms of what the problem was.
Yes, we have some from Brooke. It says it wasn't fully twisted to release. So the issue was just that particular trial in that particular moment, that it wasn't fully twisted. Thank you, Brooke.
Yeah, thank you. I have here a question from Eric, where he says, is there a plan to investigate evacuation impacts in the HEVS position from the research project 2019? So
The DART one.
The DART one, yeah.
So in short answer, not at the moment, but to give a more complete answer, so the DART investigation for the high floats came up with 2 capsize positions. One was fully inverted with the, so it would be a fully capsize, and I think maybe the results of this research project could be relevant to that because it's fully capsized. And also believe, Dave, you have more information. You've already done some.
We've already done those trials. Yeah, they're, what's the CA paper number soon? 9. we'll think of it. But we've already performed exactly those trials. We did back-to-back comparison between fully inverted and side floating, and that's reported in the CA paper 99001. Apologies for not remembering all the paper numbers from 20 years ago, but
yes, that's already been carried out.
We've already done, basically the bottom line is those trials have already been done. If you go on the CA's website, you should be able to find it. In fact, if there's any way we can put some feedback in, I'll dig that out and give you a link to it.
Or maybe it could be referenced in the final report, if it's not already referenced in the final report, which will be put on the website.
If it's not in this, I can't remember if we referenced it in this report. It should certainly be in the review, the first part of this first phase of this project. That review.
But the bottom line was that basically with the side floating concept, you removed the time pressure to escape because you have an air pocket in the cabin, so it actually doesn't matter how long it takes you to get out any longer. But I think in the trials that we did, it was, well, actually I took part in them, and I can tell you it's a doddle by comparison. Without EBS, you don't need EBS either. Yeah, that's an important point.
Thank you. Let's move on to the next question. Thank you very much, Stuart, for forwarding this from the chat. How do you, and I think it's an important one as well, how do you see the differences in the requirements for the SC VTOL, considering the differences in the expected passenger profile?
Yes, that's a very good question. So we have to look at the results of this research in context. Obviously, this is a research project aimed at rotorcraft for ditching certification. For SC VTOL, we have 3 operating scenarios we need to look at. We have the limited overwater operation, which is for restricted amount of operations over water, inland water, so lakes, rivers, etc. We have the emergency flotation operations, and we also have the ditching operations, plus some concepts if it was similar to offshore. So we must make sure that we cover the risk depending on the operation, so limited versus emergency flotation versus ditching, and also the naive passengers, and also make sure that we get the correct lessons learned. So there's a little bit to look at on that. Regarding the passenger profile, of course, the results of this research will also be used in our ditching certification, which is not necessarily offshore. So that will also be a similar passenger profile, naive passengers who have not got EBS immersion suits and haven't done the training. So that is something we must take into account. We are looking at that as we're reviewing the SC VTOL MOC at the moment. And the same for the previous research. We're trying to take the results and adapt it to the concept and risk and operations and passenger profiles of SC VTOL. It's not so easy.
Thank you. Let's move on to another question from Tim, and thank you, Stuart, for forwarding. Did the swimming in Yearbeaks report any disorientation with the inverted tests?
Sorry, could you repeat that for me?
Yes. The swimming in Yearbeaks report any disorientation with the inverted tests?
I certainly don't remember them specifically commenting. We didn't have as many comments about disorientation than I have in the past. In most cases, they used part of the helicopter cabin as a means to stabilise their position. So they either pulled themselves along the floor or were holding onto the sides of the seats. So that enabled them to make progress in the right direction. But they didn't particularly comment about the disorientation.
Good, thank you. Then I note here that Grant thanks Dave for the answer of his questions.
Oh, that's going right.
Another question from him: did the SGPs, the test subjects, report becoming more comfortable with escape as number of runs increased?
Definitely.
Yeah.
And that was just fairly obvious watching through. So again, this is one of these issues that we've discussed at length in terms of how representative the trials were. You know, we ended up with people who were well trained. That was partly built into the design of the project because we were certainly conscious that there'd only been one full escape trial done before. We were quite nervous about how it was going to do. So again, covering the risks and covering safety, it was partly built in as a method of caution. We might be brave enough if we did future trials to do it with more naive subjects, but we weren't willing to do these particular trials on this occasion with completely naive test subjects.
Thank you. Then Eric comes back with a follow-up question. Eric was the one who raised the thing with the flotation system. My question is more for CS27, where there is no side float and the emergency exit is below the water.
Yes, okay, I understand the point now. So in the DART research, it showed that for CS27, if they had a high float design, the full capsize position is the stable floating position and the emergency exit was below the water. At the moment, we don't have any intention to run any research on this. The next thing that we have to look at regarding the side floating is the rulemaking task to see if the cost-benefit analysis supports introducing it for CS27, CS27 Cat A or CS29 as initial airworthiness. As the CS27 is fully inverted, again, I think some of the results of this trial would be quite valid because the occupants are in the same fully inverted position. But it's something we will look at during the rulemaking task phase 3 when we're looking at the DART research. And that's the benefit, I think, as well of putting the two projects together into one rulemaking task, that we can cross-look at conclusions from one and test restrictions or limitations from the other one and put them together to get a good NPA published.
Thank you, Emily.
I hope that answers the question. Please put another note if I've missed the point.
Thank you. Then we have here a forwarded question from C. Kirkland. Is the escape lighting a new requirement, and is there a requirement to retrofit? Thank you.
Yes, thank you. That's for me. Part 26 was recently published with retroactive requirements for rotorcraft operating under ditching certification or ditching operations, and in that the heels lighting is mandated for underwater emergency escape exits or hatches.
Thank you, Emily. Another follow-up question from Lydia. Apologies in case I missed the point. CS27, CS29 will be updated to include full-scale underwater capsized evacuation demonstration ?
No, that's not the intention at the moment. So apologies if we gave the impression we might be considering to put that in. What we want to do is take the lessons learned from the full-scale underwater capsized evacuation to check if any of our requirements or features we've put in to support the egress of survivors from the capsized helicopter, to see if any of those need to be reconsidered. And some of the items that spring to mind immediately would be the marking on the handhold. At the moment, that's not in our AMC. And also from the task 1, as explained by Dave, maybe we need to re-look at the maximum forces for some of the mechanisms that might need to be used underwater, or we have to put in some compensating provisions. But the intention is not to ask for more underwater evacuations. It's for us to use the results of this research to see how we need to develop or update our guidance material. And also, fortunately, which is a very good result. The actual requirements themselves have been quite well validated by this research. We're really looking at an update for A and C material only.
Thank you, Emily. Now, a question which is actually familiar to me. I don't want to tell you why, but a forwarded question from Jersey. Was the water temperature taken into account? Yeah.
Well,
The colleagues don't know why we laugh, but
well, the water temperature was the same temperature that is used during normal training. I don't think the water temperature would have affected escape times per se. They do affect breath hold times.
Yeah.
Sue, anything to add?
No, I think that's a fair point. And yeah, yes, a colder water temperature would have been more representative of the real accident, but I'm not sure if there's a facility in Canada. Certainly I'm not aware of a facility in Europe where you can actually do helicopter underwater escape with a cold water facility. Training requires water temperatures to be at a certain level.
Yeah.
And also the aim was to have a look at the process of escape and also the time for escape. And again, I'm not sure if the water temperature would have made a difference, or it would have been another variable to include into the research project to make it more difficult to get conclusions that we could use.
I think the bottom line is that this is the reason why immersion dry suits are worn, is to protect the occupants against cold shock.
Yeah.
Obviously, you're still going to get cold water on your face, which isn't going to be very nice, but whether that would have affected escape time, I would have thought that would have been a secondary effect.
And also, as Brooke has put in the chat, and it might be worth mentioning who Brooke is.
That'd be a good idea.
Okay, so Brooke runs the test house at Fleetwood, which is the facility we used for all the trials. So it's Brooke's team that were actually running the research project from the practical end of things.
And she was also in the HUE2 for the underwater trials.
She was.
First time witnessing. So she's made the note that all the subjects were wearing immersion suits. And of course, with the new immersion suit ETSO that will be coming out based on the new standard, there'll be different immersion suits depending on the temperature of the water. So that should compensate for to some degree, to different temperature of water.
Yeah. Good, thank you. Last question from Jonas. Are there tests being conducted regarding variable sea conditions? Are they likely to affect the outcome of an evacuation?
Yeah, I mean, this is something that this is a consideration, particularly for side floating, where you've got more of the aircraft exposed above the surface. With the aircraft fully inverted, I'm not quite sure how much motion there would be. As part of some research CAA did on involving wave tank trials of the side floating concept, we did include accelerometers in the model and look at accelerations inside. That was really from the perspective of the side floating scheme. We didn't really look at that from the fully inverted helicopter. I think anybody that's been scuba diving probably knows that once you get below the surface, you're relatively immune to wave action. And with the helicopter fully inverted, there's not much exposure to waves. There's no fuselage above the surface. So it's an interesting point. I wouldn't say there's no effect, but...
No, it certainly would affect survivability once people have got out there. So you've got the two phases. One is getting out of the helicopter, and then it's survivability while you're awaiting rescue. So it would certainly impact people's ability to get into life rafts, drowning. And once you've removed the mouthpiece from your EBS, you're at a much higher risk of drowning, particularly if there's breaking waves. Yeah. So overall survivability, yes. Yeah. Possibly less so in terms of the actual escape process. Mm-hmm.
Thank you, Dave and Sue. And we have one last question. Thank you, Stuart, for forwarding this one. It's from Mattison. What are your standpoint regarding using rebreather lung that cannot be deployed underwater in offshore crew change?
Well, there's a simple answer to that. It's not compliant with the UK Aerops regulations or the answer. So it's non-compliant, so not acceptable.
Okay.
Yes, we were really testing the European rules in this research project, so we limited our scope.
And in terms of approvals of new emergency breathing systems, they now have to be deployable underwater to meet the specification.
What we call category A, which means deployable underwater in under 10 seconds. So if it's not deployable underwater, it doesn't pass muster.
Yeah.
In fact, we did have a category B at one point, but then we removed that, didn't we?
Which potentially could have met the requirements.
Yes, but that got removed.
Yeah.
Good. Then I mark also this question as completed, and I don't think, Stuart, we have any other question on the webinar chat. So thank you very much, Sue, Dave, and Emily, for your answers. Also, many thanks to Brooke, who assisted us from the UK. Thank you very much also, Stuart, for your support. Colleagues, we come to an end. Before I release you, just one additional remark from my side. Colleagues, we as an authority, and I have to say, when I say authority, we actually talk about authorities because we work very closely together with the national aviation authorities. And with the national aviation authorities, we have prioritized future research needs. Yeah, quite many, but we have broken them down into 9 areas. I just quickly go through them that you know. We are looking also for future projects. They are across all areas for which authorities usually are responsible for. You see here, for example, the first one in the field of environment, where we would like to support the production of sustainable aviation fuels. And one way to do that is that we find new production pathways. So one project on that. Another one is dealing with artificial intelligence, looking here in particular on the human factors side. Security, 2 topics. One, how can we use artificial intelligence tools for the use to increase or enhance security? And the other one is dealing with developing a methodology to assess the risk of conflict zones for aircraft operators. Then, in the field of health and medical, also 2 topics, one dealing with the impact of obstructive sleep apnea, and the other one is focused on high airspace operations. High airspace operations impact for the flight crew, but also for the passengers. Then, on automation, what is the increasing level of automation? What is the impact for the flight crew and for the air traffic controllers, including actually what are the legal implications of that? Who, for example, would be responsible, who takes over the responsibility of the commander if you have an automated system? Then, in the field of air ops, you know, we have currently a research project dealing with enhanced minimum crew operations. And we believe that when actually such operations will start, that we need, and we can gain already some data from day-to-day operations, that we have to look also here on the flight time limitations, and also here actually on the medical aspects of the single crew. Then on ATM ANS, 2 topics, one dealing with the performance of ground equipment, which is linked actually to the certification of ground equipments. And the second one is dealing with airspace classifications in the lower airspace. On drones, focus is now on BVLOS operations, particularly also on see and avoid applications. And last but not least, data for safety, which is our big data program, which we would like to use in order to enhance our safety risk management scheme. You see here 2 documents. These documents will be uploaded very shortly on our website. We have sent them to the European Commission so that these topics can be considered in future Horizon Europe work programs, and we hope that also we will soon be able actually to launch new tenders for new research projects, and we would be grateful if all of you would participate in such tenders. So that's everything from me also now. So let me once more thank, first of all, the panelists. Sue, Dave, Emily, thank you so much for your presentations, for answering your questions. I would like to thank you, colleagues who were online, for your very good questions, making the whole webinar really a live event. I would like to thank my colleague Emily and her team, also Lionel, because you have done a great job on our side, worked together with the contractor and achieved here really good results. So many thanks also on the CAI, who was an excellent contractor with excellent results. Thank you very much for that. As already said, we will upload the recording as well as the presentation, hopefully by tomorrow. And I'm confident that we can upload the final deliverables next week.
Shortly, yeah.
Shortly, shortly. So next week, perhaps it will be within 10 days, but certainly you will see the final reports very soon uploaded as well. Thank you so much for joining us, and I hope, or we hope, that we will see you very soon again. Take care. Bye-bye.